stopping the recording. All right. Very well. So we can now continue with our discussion regarding the transformations and their applications to compression. The transformation in 2 dimensions is a little bit more tricky, as I say. In terms of the definitions, actually, it's not very difficult. We can say that in 1 dimension, we can write V is equal to A times U. A is a matrix, and U is the input vector, and V is the output vector after the transformation. A is the transformation matrix. But we have to roll back to our original definition in the form of a summation to see what's going on in 2 dimensions. And we can extend this to 2 dimensions like this. We can say, for example, V of K and L. Now we have 2 parameters because it's an image, it's 2-dimensional, and it's finite, capital N by capital N. Let's assume a square thing because then the matrix multiplications will be easier. We can write it like this is a double summation this time over M, let's say, and N. We have U of M and N, which is a 2-dimensional image. So its transform is also 2-dimensional. And UMN is the original image that we have, which we are trying to transform. Now, at the right-hand side, we can write it like A sub K and L of M and N. So essentially, we don't have a matrix here. We have a 4-dimensional entity, which can be considered as a tensor or something like that. So we can't really write this equation as in the form of a matrix and vector multiplication that we did for this 1-dimensional case, because this is 4-dimensional. It's like multiplying a 4-dimensional tensor with a 2-dimensional matrix and obtain a 2-dimensional matrix. But in the linear algebra concepts, how can we proceed with this? And the way to proceed with this is possible if this could be split into or separated into normal regular matrices in the form like instead of A and I will use B here because I don't want to mess up with the same notation, and C sub L of N, like this. So this multiplication would correspond to the 4-dimensional or 4-parameter expression of AKLMN, A of KLMN, 4-dimensional. Instead of that, I'm splitting it into a 2-dimensional matrix, BKM and C of LN, all right? If I can write it like this, it means I'm splitting 1 dimension corresponding to M and its transform, which is notated by K, M and K, separating it into 1 form, which will be concerned with the rows of this U matrix, because I will only consider U of M, for example. And then this CLN is taking this L and N parameters only, which is making a transformation of the columns of U of Mn. So I will be considering like U of N in the column format only. And it depends on how you express the column and the row, by the way, for an image. So it may or may not correspond to the column of the image. It may be a row, whatever. The N parameter is transformed by ALN in such a way that the output will be V of L, whereas if I use bkm and u of m only, it will generate v of k, this part, the first part. So the row-wise and column-wise processing will be split. But it's possible only if this four-dimensional entity tensor can be written as a multiplication of two matrices parameterized by k and m at one side and l and n at the other side. If you just generate any four-dimensional tensor and then try to separate it, split it into b and c, that would be very difficult. It may be even impossible. For some cases, you just won't be able to do that. So we usually start from the opposite side. We generate a transformation in one dimension, let's call it B, okay? And this C is the same as B, by the way. It's just applied horizontally and vertically. So I will use this for the rows and this for the columns, for example, to construct a hypothetical four-dimensional tensor concept. So we don't design a four-dimensional tensor. We design a normal matrix for the transformation, a transform matrix. We design it. For example, the Fourier transform is that, one of that. We will see a few more transformations that are suitable for compression purposes. And then we multiply it with the other direction, and we say that it becomes now our transformation kernel in two dimensions. So we start from the first, the one-dimensional case, and we proceed to the two dimensions. That's the way that things are designed. Now, if they are separable like this, then we come up with a separable notation of this V, K, and L is equal to summation over M. And I'm going to put B sub K of M here because it has nothing to do with N. Therefore, I can push it from the left-hand side out of this summation, N from 0 to capital N minus 1. U M N and C sub L N. Okay, I can write it like this. Now here, for once, I would like you to not consider this. Okay, just ignore it for the time being. Let's assume that that is U of N only that we have here, U of N. And then I have C sub L of N. Then it becomes a one-dimensional transformation. This summation becomes a one-dimensional regular transformation. But it is transforming only the second parameter, let's say the columns of U of N. And for each row, we have different columns. So it is like a horizontal way of making a process of U of N. We have M. We have many of those things. M is freely changing from 0 to capital N minus 1. But for each of them, we have a one-dimensional U of N. For every M, we have a U of N. And that U of N is converted using this transformation, transformed. And that transformation output is, it essentially becomes something like this. The U matrix multiplied from the right-hand side with C transpose. Actually, it's not from the left-hand side I'm doing because I'm applying it to the second parameter. Since it's the second parameter, it's like multiplying from the right-hand side. And that right-hand side multiplication or application of a transformation, when I put the transform matrix to the right-hand side of a vector, I have to take the transpose of that transform matrix, C. So that's why I'm using C transpose. Sorry. This C transpose. And it is being applied to the rows of U. So the rows of U are multiplied by a transform matrix, transpose of a transform matrix. Previously, we were multiplying the transform matrix from the left-hand side, and at the right-hand side, we had the column vector. Okay, but now it's a row vector. So since it's a row vector, I have to put it first, and at the right-hand side, I'm just transforming with the transpose of this C. And once it is achieved, at every row, everything is transformed, but the columns are not transformed now yet. So the columns need to be transformed, and that is parameterized with in terms of M only. So we ignore N, okay, the horizontal variation, the column variation, we ignore. We only consider M this time, because now I have this transformation. BKM is B matrix multiplication to a column vector. The column vector is here, but there are many column vectors. Okay. And when I multiply with those columns one by one, I come up with this time the overall transformation, which is like B matrix from the left-hand side to act on the column vectors of the output from the previous stage, which is U times C transpose. Okay. So this is the V output matrix. We can apply the two-dimensional transform like this. C transpose is transforming the rows, and B is transforming the columns. And of course, usually B and C are the same. We don't expect to use different transformations for the rows and another different transformation for the columns. We don't do that. We usually apply the same transformation. And using the previous notation, usually we have this. V is equal to the A transformation matrix times U times A transpose. And that's it. This is our transformation in two dimensions. We transform from the left-hand side and from the right-hand side using the transpose of the same transform. This is a two-dimensional transform. So if you have an A transformation, you can just apply it like this, and it will correspond to the two-dimensional transformation of U in the form of a matrix. If it's not a vector, but if it's an image, then you can do it like this. And of course, correspondingly, U will be like A inverse times V times A inverse transpose, right? Because from the left and right, we have to invert these matrices so that we obtain the inverse transformation from V back to U. But if A is a unitary matrix, then A inverse will be A conjugate transpose. And then I'm going to have V. And the transpose of my conjugate transpose will be A conjugate. So the inverse transformation is usually taken by simply applying a conjugation of the A matrix. Now I have to put a remark at this point for MATLAB users. You have to note that if you put a prime or a transposition, not transformation. It's not trans, I guess, it's tran, it must be. I'm not really sure about the notation, I forgot. Just check it using MATLAB. Transposition, that's what I mean. The superscript of capital T, the transpose of A, actually corresponds to A conjugate transpose. It automatically conjugates and transposes. So be careful. For example, if you want to apply this, if you use prime or a tran operation for transposition, it actually makes conjugate transposition. But as you see, you don't need the conjugate transpose, you need the transpose here. And in that case, you have to conjugate once again. You have to put conj in parentheses, tran in parentheses, a, to come up with essentially the transpose. Okay, that's critical and important. Otherwise, when you're using MATLAB, you fall into a trap. Okay? MATLAB intrinsically already makes the conjugate transpose if you say transpose only. So be careful about how you do that. Now, in 2 dimensions, however, we also have a basis interpretation. Now we can continue with this. Basis interpretation of 2D transforms. What do we mean by that? The basis interpretation was like this. We have a V vector to be equal to U1 times the first column of A1, 1 up to A1 n plus U2 times A21 up to A2n plus etc. all the way up to not A, it's UN times AN1 up to ANN. Okay, this is what we have. It actually means A times U. Okay, this matrix vector multiplication essentially corresponds to this kind of notation. That's why we are saying that A is essentially the new basis for the representation of V. Actually, we were doing it in the reverse way. We are usually representing U in terms of V. So let me also write it that way. U is like V1 times the first basis vector, let me call it E1, plus V2 times the second vector E2, plus all the way up to Vn times E sub n, the last basis. So this is, defines the representation of U in terms of a new basis of E1, E2, all the way up to En, which will form A inverse matrix. So if you stack them up like this, E1, E2, all the way up to En, this matrix is supposed to achieve A inverse matrix, or you can call it, let's say, B matrix, whatever. So this is our unitary matrix, which corresponds to the basis elements. Now, in this kind of a new basis, instead of using 1, 0, 0, 0, 0, 0, 1, 0, 0, 0, 0, and then 0, 0, 1, 0, 0, etc., which is the identity basis that we are having, the trivial basis, which is already the basis that is used for the representation of U itself. The U1 will pick the first one, U2 will pick the second one, etc. But instead of that, we can make a rotation of these 1, 0, 0, 0, 0, 1, 0, 0, etc. Basis vectors. We can rotate them, and we can come up with a new set of basis vectors, E1 up to En. So utilization of this new basis may have its benefits. The benefits are usually considered in terms of compression efficiency. For example, if V1 is large, V2 is large, but all the other Vn's are small, very little, then we can get rid of them. We can just ignore them, which means I'm making a compression from an n-dimensional U space to only 2 elements. From n items to 2 items only. I can make a representation, and the others I can ignore. Very simply, I can ignore. And it will be a tremendous compression from n to 2. Let's say n is equal to 16. And from a 16 element U vector instead of that, I'm using only 2 elements. 16 to 2 compression. It's a huge compression, but at the expense of some loss, of course. And what is that loss? It's the loss is the ones that I do not use. And if they are small, then the error that I make with this lossy compression will be small. That is a fundamental way of looking at a lossy compression. I'm not using some of the transformation domain elements. A very good example actually is the Fourier transform. Suppose that you have a low frequency signal, a low pass signal. When you take the Fourier transform of it, it will be contained in the low band. And let's say that I'm not using the high band because the signal values at those high bands are very small anyway. So I chop them off, which corresponds to low pass filtering, very simple low pass filtering. I just take within a box the low frequency contents, and then I reconstruct, take the inverse Fourier transform and look at the signal. What kind of a signal will I see? It will be almost the same signal. Maybe a little bit blurred, smoothed out. Therefore, the loss here is regarding some of the details. Some sharpness will be lost, but it's way better than getting rid of the items. Suppose that it's 16 to 2 compression like this. It's like getting rid of 14 of the samples. If from this time data, if you just chop off 14 of the samples and keep only the 2 samples, it will be catastrophe, right? The signal is lost. All of the signal is gone. But if you take the Fourier transform and then chop off 14 of the samples in that domain, which means you are not using these 14 samples, but you are retaining these 2 samples from the Fourier domain with the basis of the Fourier transformation, it will become low pass only, but the signal will still be tolerable. And people just do this kind of an approach in compression, in transform domain, in lossy compression particularly. All right, now I want to give you a 2-dimensional example from this one. In the 2 dimensions, the situation is a little bit different. It will be like U will be a 2-dimensional matrix. I will be trying to illustrate, let's say, a 4x4 image, a very small image here. And this will be equal to, this is the U image. This will be equal to something like this, V11, the first V item in the V matrix, the top left corner, times the basis matrix of E1. E1 is here, and E1 is itself, as you see, a matrix, an image. Okay. So it's not a vector as we did before. It's a basis image. E1 is a basis image. And then plus V1, 2 times, by the way, this is E11. E11. V1, 2 times E1, 2, another basis image, plus etc. all the way up to V 4x4 times the last basis image that we have, which is V for, sorry, it's not V, it's actually E44 basis image. For example, for this representation of a 4 by 4 image, how many basis images are we using? How many basis images are we combining to come up with a 4 by 4 U image? Can any of you guys tell me about that? So how many basis images do we have here? I'm expecting an answer at this point from you.
Maybe 16.
Yeah, it's exactly 16. We need to have 16 basis images. Let's use the trivial transformation to see why 16 images are necessary. For example, if you have an image like this, again consisting of 16 pixels, it's essentially equal to a value, let's again call it V11 times the first basis image that I'm going to use will be now. Notice what I'm going to draw. It is 1 here, okay, and all the other pixels are zeros. And then plus V12 times the second basis image will be 1 in the second pixel in the raster scan order, and all the others are 0. So the basis images are essentially ones at the position of the raster scan in the first row, 1, 2, 3, 4, and then in the second row 1, 2, 3, 4, in the third row, and the last row 1, 2, 3, 4. So plus blah 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 plus the last one will be V4 times the last basis image will be 1 here in the at the last corner. So I'm tracing the image from the first to the last. If I consider it like this, then of course this V11 will have to be exactly the same as U11 because it's the first pixel, right? And this V12 will be exactly the same as U12, the original pixel values. So this transformation is not a transform, it's an identity transform that we have in 2 dimensions. And by the way, why is this U11? Let's say that this is V11 and U11 is this corner pixel. What is this? How do we evaluate this thing? By taking the inner product of this and this, which is the inner product of U and E11. We have to take the inner product of these 2 matrices. And when we consider the inner product in multiple dimensional entities, it's no different than 1-dimensional entities. We just term by term, pixel by pixel, multiply everything. So we multiply this E basis image with our image term by term, and then add them up. So when you term by term multiply, this corner will be multiplied by 1, and every other pixel is multiplied by 0. Okay, all the others will be multiplied by zeros. And you sum them up. You should normally take the conjugate of the second one, this one, but it's a real matrix, so the conjugate of it will be the same. And when you do that, only the first one will be multiplied by 1. When you sum them up, that first item will be depicted. So this inner product will give you U of 1 and 1, which is this corner point. Similarly, this one will give you the second pixel, which corresponds to this pixel here. Okay, that's how we come up with these transformations. But this transformation is not a transform, as I say. It's just the normal representation or an identity transform. We have to be looking for more exotic transforms or more useful ones, not being exotic, of course, more useful transforms. In 2x2 case, I will try to give you an illustration of what kind of benefits can we get in compression. And it will be the transformation basis that I will think about and try to construct. So I will be trying to compress efficiently using transform coding. I will try to efficiently transform this image, which is 8, 10, 12, and 14. Okay, yeah, let's say that this is our image. All right. And I want to express it in terms of some basis images. 4 basis images, essentially, are necessary for this. The first, the second, the third, and the fourth basis images. And I will design these basis images heuristically. Sorry for this noise from outside. It's the water delivery in this lockdown. First, I will indicate what they are. They will be 1/2 in parentheses. So every value is multiplied by 1/2, 1, 1, 1, 1. And I will be claiming that they are bases, so they must have unit norm. The norm, the square of the norm, I will indicate by taking the inner product with itself. So let's take the inner product of this first basis, so-called basis image with itself. It's 1/2 here, 1/2 here, 1/2 here, 1/2 here. So I will multiply with itself. It will become 1/4 plus 1/4 plus 1/4 plus 1/4. So I have to sum up the multiplications, and 4 of those summations will give me 1. So its norm is square root of 1, which is 1, and that means it's normal. The other basis images must be orthogonal to those things. And I will try to obtain those extra basis images to become orthogonal to this one. So I will choose it like 1, 1, minus 1, minus 1. Is this orthogonal to the first? Again, term by term, we multiply 1/2 times 1/2 plus 1/2 times 1/2 plus 1/2 times minus 1/2 plus 1/2 times minus 1/2. So as long as the number of plus ones and minus ones are equal, when I sum them up, actually it will give me 0. So this and this are orthogonal to one another. Besides, if I multiply every term by itself and sum up, this will still give me 1. So it's orthogonal to the first one, and it has unit norm. Good. That's a good thing. And then I will have 1/2, 1, 1, minus 1, minus 1, which must be orthogonal to both the first and the second one. Its norm is 1. We can at least clearly understand that it's unit norm. And it's orthogonal to this one. I can see that the left and the right will cancel one another, being positive and negative. How about this one and this one? The first multiplication will give me positive. The second will be negative. This one will be negative. The fourth one will be, again, positive. So half of the time, the multiplication becomes negative. Half of the time, it becomes positive. So the inner product between these two is also 0, which means this is normal and orthogonal to this and this. And finally, this will be my last basis image. And of course, with a 1/2. Its norm is 1. We know it. It's clear. And it's orthogonal to the first one. Is it orthogonal to the second one? Let's see. 1 times 1 positive. 1 times -1 negative. -1 times -1 is positive. -1 times 1 is negative. So half, half, they cancel, inner product 0. With this one and this one, this gives positive, the first one. The second one gives positive. The third one gives negative. The fourth one gives negative. So half of the time it's again negative. The inner product of this and this is also 0. So I come up with 4 orthogonal and unit norm images of size 4. Size 4 means if they have 4 pixels. So they are supposed to span the 2 by 2 or 4 element pixel space with some coefficients. Let's call these coefficients A, B plus, of course, plus C plus D. So A times the first basis image plus B times the second plus C times the third plus D times the fourth basis image is equal to this. So what is A, B, C, and D? Normally, if I just come up with any 4 linearly independent 2 by 2 matrices, which I could use, but then the development of A, B, and C, and D would be very difficult. But since I come up with an orthonormal set, I know that from linear algebra, I know that A is equal to the inner product of this, which is U, the image, and the first basis, this. So A is equal to the inner product of this and this. So what are their inner products? Every value is 1/2 here. So let me add these numbers and divide by 2. That will give me the inner product. So it's 8 plus 12, which is 20, plus 10 is 30, and plus 14 will give you 44, right? Half of it is 22. So A is supposed to be 22. So it's 22 times the first basis. And what is B? B is top 2 numbers are 1s, bottom 2 numbers are -1. So I will add up this, which makes 20. And the bottom ones will give me 24. 20 minus 24 is -4. And with this 1/2, it is -2. So B is -2. Let me see what is C. For this, I have to add up these 2 and subtract from them the second column. So 8 plus 14 is 22. 12 plus 10 is also 22. Ah, that's good. So 22 minus 22 is 0. Over 2 is still 0. So this C is actually 0. Very nice. I'm glad. Okay. And then for the last one, I have to add these diagonal terms and subtract the other diagonal terms. So 8 plus 10 is 18. 14 plus 12 is 26. 26 minus 18 is 8, right? And over 2 is 4. It's a little bit more than what I expected in my mind. It's 4. So the new transform could be imagined like this. You had a previous representation of 8, 12, 14, and 10, and you transform it to a new transform domain whose values are 22, -2, 0, and 4, like this. From
Excuse me.
Yeah.
It's actually -4.
-4. Is it -4? Yeah, it is. It is -4. 18 minus 26 is -8. Over 2 is -4. That's right. So let me correct it. That's right. It's -4. Okay. So from the left numbers to the right numbers, I made a transformation. Now the question is that a good transformation? And is it good for compression purposes? And the way to look at it is, by one by one eliminating those coefficients from the right to the left. And while we are eliminating them, how much error do we make? Meanwhile, we eliminate in a similar manner the originals and compare. For instance, suppose that I eliminate this one. When I eliminate it, it means I'm replacing it with 0. I'm substituting it as with 0. Since the value is unknown to me, I assume it's 0. So what would be the reconstruction if I have 22 minus 2, 0, and 0? That would be my reconstruction in that situation. For a compression of 4 to 3. So the input has size 4, the output has now size 3 because I eliminated one of them. So 4 to 3 compression rate, that's the compression ratio. And at every compression ratio, I have a corresponding amount of distortion. What is the distortion that I have? For that, I have to reconstruct from these, and I have to eliminate the contribution from this one. If I construct from this one, it will be all 11, 11, 11, and 11. And then the tops will be -1, -1, and +1, +1, because this is -2 with 1/2 of this. It will be -1 times this. So 11, 11, 11, 11, -1, -1, +1, +1 will give me 10, 10, and 12, 12, right? And then I need to, of course, add this one too, but it's 0, so nothing. The reconstruction is therefore, again with a blue, let me say, oh, it didn't become blue. Yeah. So the reconstruction will be 10, 10, 12, and 12. This will be, you may call it U tilde. It's an approximation of the original. So how good an approximation is this one? What kind of an error did we make? What is the distortion, mean squared error, for example, between this original and this reconstruction? How do we calculate it? The calculation is simple. We have been using it all over for our lossy compression techniques. The amount of loss will be calculated like this. The first item minus the second item, which is -2. We take the square of it. It will give us 4. So 4 will come from here. 12 minus 10 is again 2. Its square is 4. 4 again from here. 14 minus 12 will give me 2. Its square is 4. Again, 4 is contributed from here. And 10 minus 12 is -2. And its square is again 4. So all of these pixels will have a distortion of 4. And when I add them up, it will give me 16. 4 plus 4 plus 4 plus 4. So the distortion is equal to, it's square distortion, by the way, is equal to 16. Okay. If I eliminate the last one, is this a good distortion? You must compare it with this kind of a situation. So we eliminated this one and we obtained d squares equal to 16. So we eliminate correspondingly this one, for example, 1 pixel from the original image. So how much distortion does it make? Very simple. If 10 is gone, the square distortion from that is square of 10, which is 100. So instead of 100, now, if I eliminate 1 pixel from the original image, I would have a distortion of 100. Now, I first transformed and then eliminated 1 pixel from this red suit. I eliminated this one, and my distortion became 16. So 16 is significantly smaller than 100, of course. But it will be more dramatic if I eliminate even more. For instance, let us also eliminate this one. Furthermore, on top of -4, now I both eliminate -4 and 0. And I again replace it by 0, whose original value was already 0, and the reconstruction would be the same, 10, 10, 12, and 12. So the square distortion will be equal to, again, 16. But when I eliminate 10 and 14, what's the square of 14? What's the square of 14? Can you tell me? There must be some students over here.
Yes.
So what's the square of 14? I couldn't evaluate.
196.
Well, 196. So the square distortion will be 196 plus 100, because it must eliminate 114 altogether, which will be 296 altogether. So compare these two now. Right? And if you go on, actually, it will be even a better comparison. Suppose that you eliminate this one, then your reconstruction will be from here only. It will be 11 everywhere. 11, 11, and 11. So what is the distortion between, so I'm eliminating every other thing, all of these three coefficients I'm eliminating. And my representation will be only from the first coefficient, which is 11, 11, 11, 11. When I compare these two, the distortion, square distortion will be, with 8, the difference is 3, so it will be 9 plus. From 12 to 11, it will be 1 plus. From 14 to 11, it will be 3 squared 9 plus. From 10 to 11, it's 1 again. So it is 20. So the distortion, the square distortion, if I further eliminate this one, will be 20. Whereas if you further eliminate this 12, then the distortion, square distortion, will be 144 plus 196 plus 100, which is 440, I guess. So compare this distortion with this distortion. Of course, you don't want to have a distortion by just chopping from the pixels. So instead of that, you first transform and chop off from the transform values, and the distortion will be significantly less, as far as I can see. And of course, if you chop from the pixels, the image will be lost. By the way, with this kind of a distortion, the compression ratio is 4 to 1. It's a huge compression. You compress to 1/4, a quarter size, as compared to the original. And this square distortion is only 20, which is a good figure. But why did we have this kind of a good figure? Why did it work? Because I have judiciously, cleverly designed my basis images. I know these basis images, by the way. And I have deliberately designed an input so that the pixel values are having strong correlations within one another. They are strongly correlated. If the pixel values are strongly correlated, so you don't expect a huge number and then a very negatively huge number and things like that. Just the opposite way of making a correlation. Or if they are totally uncorrelated, if one is positive, the other one could be positive or negative or 0. So we don't have any correlation among the pixels. Of course, this kind of a transformation wouldn't work. But it works for some nice cases. And those nice cases are the cases where we usually apply. For real life images, for example, for real life scenery, consider an image where there's a scene consisting of a grassland. So the grass is green and it's green everywhere. You see, it's less green or more green, darker or brighter, but the correlation is a lot. The correlation between neighboring pixels is a lot. If you have such strong correlations, then applying this kind of a transformation would be good. This transform that you see, which produces these basis images, are actually corresponding to the basis vectors in normal one-dimensional data, corresponding to a transform matrix, which is equal to this: 1 over square root of 2, 1, 1, 1, minus 1. This is my transformation matrix in one dimensions. And how did I obtain these basis images? I obtained those basis images by taking the outer products of the columns of these of this transform matrix. Actually, the inverse of it. First, I take the inverse of it, which is the same. What a coincidence. You can check it if you wish. A inverse is the same. And this gives me the fact that this is equal to E1 and E2 basis vectors. So what are these basis vectors? E1 is 1 over square root of 2, 1 over square root of 2. And E2 basis is 1 over square root of 2 minus 1 over square root of 2. Are they basis vectors? Yes, they are certainly basis vectors because they have unit norm. When you take the norm of it, calculate the norm of it, square of the first term plus the square of the second term is 1 over 2 plus 1 over 2, which is 1. So you take the square root of 1, it will still give you 1. The norm of E1 is 1. The norm of E2 is also 1. And E1 is clearly orthogonal to the second one because of the positive negative cancellations. So from linearly independence or from orthogonality, actually, these two vectors with size 2 will span a two-dimensional space. So it's a basis. These are a basis. In fact, they are the 45 degrees rotated versions of the original basis vectors, which I will call F1 and F2, let's say. F1 is equal to 1, 0. F2 is equal to 0, 1. Okay, let's call it that way. If I rotate them by 45 degrees, then I will come up with these new basis vectors. They are 45 degrees rotated versions, E1 and E2. E1 will be equal to 1 over square root of 2, 1 over square root of 2, and E2 will be equal to 1 over square root of 2 minus 1 over square root of 2. So making a 45 degrees rotation will give me, again, rotation of basis vectors will give me another set of basis vectors. By the way, this rotation from linear algebra, you may remember, has this kind of transformation. E sub n is equal to a rotation matrix times F sub n. For example, E1 is equal to the rotation matrix times F1. And the rotation matrix is cosine theta, sine theta, sine theta minus cosine theta for the rotation of theta degrees. If theta is 45 degrees or pi over 4 radians, then notice that if you substitute theta is equal to 45, it will give you this. So let me indicate it. It will give you this or this, which are the same. So a 45 degrees rotation of bases is my transformation essentially. Why did I use a 45 degrees rotation? Because I was claiming that this axis representation and this axis representation, which are the first and the second items of my vector, let's call them x vectors, x1 and x2. So the correlation, the cross correlation between x1 and x2 is large. So along the x1, x2 axis, this is x1, let's see, this is the x2 axis. If I have a lot of data, if I render these data on these axes, if x1 is large, for example, then x2 will also be large. If x1 is larger, then x2 will also be larger. If x1 is small, then x2 will also be small. If x1 is negatively large, then x2 will also be negatively large. So I will have this kind of an ellipse shape on the x1, x2 axis, which is notated for data scattering. It's called a scatter plot. If x1 and x2 have the same energy, which means it's a stationary signal, so the two neighboring pixels or two neighboring samples don't change the statistics. Their energies, their variances, their square values, their means, etc., they are all the same. So if it's a stationary signal, then the slope of this scatter plot must be 45 degrees. If x1 has larger energy than x2, then it may be tilted, but it corresponds to an unstationary sequence. So x1 is larger always than x2. Yeah, it may happen. But from real life experiences, we consider a stationary random process. So if this is stationary, then the slope of this scatter plot, the major axis of this scatter plot will be 45 degrees. The original basis was this and this, which is a redundant basis because it shows equal energy from x1 and from x2 sides. So this is f1 and f2. So f1 and f2 basis vectors were redundant basis vectors. If you eliminate f2, for example, you lose a lot of it. You lose half of the data because the representation of any point, let's say this point, this is a point of interest, we want to represent it. If you want to represent it with x1 only, it means x2 you will assume 0. So it's a projection onto this point. This will be your representation using f1 only. And how much error will you make? This is your error that you will make. However, if you rotate your axis by 45 degrees and you obtain E1 and E2, I'm sorry. So E1 is here and E2 is here, 45 degrees rotated versions. Suppose that you are eliminating E2 completely. So how much error will you make for projecting this green pixel? That green pixel will be projected into this point. Let me zoom a little bit. It will be projected to this point here, and it will make only this much error. And you see the second error amount is significantly less than this error is significantly less than this error. And it's all because of the assumption that the cross correlation between x1 and x2 is large. They are strongly correlated. So if you have this pixel, for example, you have to compare the error between this size and this size. Or if you pick this point, of course, you must extend this axis. You have to compare this much error to this much error, which is projection onto this 45 degrees line. So by rotating by 45 degrees, we are doing an amazing job for such signals. And those such signals are essentially everywhere. In all of the physical reality, in most of the cases, for normal signals, we come up with this kind of a correlation situation. All right. Okay, we will continue with these discussions. They are strong and important discussions. It will give us an idea about how can we extend this to higher dimensions. This is only for two-dimensional case. We can see it's 45 degrees, but if it is 3, 4, 5, etc., hyperdimensional, we cannot really visualize those rotations. And usually those rotational things will become more complicated. We will not be easily indicating a rotation like this, cosine, sine, sine minus cosine rotation. It will be different, and it must be optimized then. Stationarity will not be sufficient. We must take a look at the correlation scatter in higher dimensions, and we must find the major axis and assign it to become the first axis. And then we will be looking for the second major axis in the hyperdimension, which is orthogonal to this dimension, but still has a lot of variations. And then I have to find the third one, which is orthogonal to first one and the second one all together. And it must be showing still among the higher dimensions the most variations, and reducing the variations one by one, eliminating the variational error amount. In higher dimensional cases, how are we going to do that? It's a systematic way. There's a systematic way of doing it, but we are way out of our time. So I'm going to stop at this point, and we will continue with this very important discussion of how to optimize a transformation next week at the same hour. So I'm stopping at this point. Do you have any questions? If you don't have any questions, we will just meet next week at the same place, same hour. Any questions?
No, thank you.
All right. So then see you. Take good care. See you next week.
See you.
Bye.
Have a nice week.